Hi again. In this lecture you will learn how to determine the powertrain's operating range. We start from the operating range of the engine in a torque and shaft speed diagram and use the transmission model and the gear ratios to calculate what operating range the complete powertrain will have in a force speed diagram. In a previous lecture, we have derived this transmission model, which links an operating point for the vehicle to the corresponding operating point of the engine, or vice versa. For this analysis, we assume a powertrain with a 5-gear manual transmission. The gear ratios range from 3.7 on first gear to 0.74 on fifth gear. After the gearbox, there is a final gear with ratio 2.7 and a wheel with radius 0.3 meters. The gasoline engine used in the example has this specification. Here we can see both the engine operating range and its specific fuel consumption, together with some key engine parameters often used to describe an engine's performance. In this analysis, we don't focus on the fuel consumption values, and we will only look to illustrate the possible operating range in torque and shaft speed, like this gray area. The engine has a peak torque of 207 Nm at 3,500 RPM. And it can be found in the engine's torque speed diagram. It has a peak power of 100 kW, which is at 5,000 RPM. The minimum engine shaft speed is 900 RPM and the maximum speed 6,000 RPM. Notice that the diagram with the operating range actually gives us all the information in the specification to the right and more. So the engine torque speed diagram is a much richer specification than the normal way of just listing a few parameter values for the engine. These are the two equations of the transmission model. We can simplify the equations by introducing a total ratio, C-TOT, from road to engine shaft. The total ratio is defined like this, and it includes total gear ratio as well as the wheel radius. With the parameters for the investigated transmission, we can put values in the equation, which results in the following total ratios for the 5 gears. They range from 33.3 to 6.67 on the different gears. Notice the unit 1 per meter. It comes from the fact that C-TOT represents how many radians the engine shaft has to rotate when the vehicle rolls 1 meter. The unit can also be written as radians per meter, but since radians are dimensionless, in practice it becomes 1 per meter. Each point in the engine torque shaft speed diagram can be translated into a corresponding operating point in the force speed diagram. First, let's consider when the gearbox is in second gear. The total transmission ratio is 1 per meter in this case. The first operating point in this analysis is maximum engine torque at the minimum engine speed. The corresponding speed in the force speed diagram is found by taking the engine speed, expressed in radians per second, and divide it with the total transmission ratio. That results in the corresponding vehicle speed in meters per second. Next, the engine torque in Newton meter is multiplied with the total transmission ratio to get the force at the wheels in Newton. That gives us this operating point. We can repeat this translation for the maximum engine torque at maximum engine speed, which we find here in the force speed diagram. 0 torque at maximum engine speed leads to this operating point, and 0 torque at minimum engine speed leads to this operating point. Maybe you see the pattern. If we were to repeat this for all operating points on the border of the engine operating range, what would that look like? Of course, the result is a scaled version of the operating range in torque speed, having the exact same shape but different height and width in the force speed diagram. We only used the 4 operating points to illustrate how we can find the operating range in force and speed. They should not be included when we want to show the operating range. We repeat the translation of the engine operating range, but now for the first gear, having a total transmission ratio of 33.31 per meter. The first operating point translates like this. Notice that the higher transmission ratio leads to a higher force than what we got on the second gear, and at the same time it is at a lower speed. The next operating point is here, and the third is here, and the final one is here. The result is again an operating range of the same shape as the engine's operating range in torque and shaft speed. This time the shape is much higher in force, but more narrow in speed. So, this is the operating range for the first gear. If we now repeat this translation for all gears, we get the following results for second gear, third gear, fourth gear, and fifth gear. The total possible operating range is the total envelope when they are all plotted in the same diagram. The 5 gears cover a large operating range, but notice that the powertrain does not seem to have any possible operating points at really low speed. The reason is that not even the first gear has a high enough ratio for the vehicle to be able to drive slower than about 10 km per hour when the engine is at its minimum speed. The solution to this is to use the first gear, but open the clutch and let it slip. That allows a lower vehicle speed while still being able to transfer the torque from the engine. Adding the possibility to use a slipping clutch, the powertrain can now operate at all speeds from 0 and upwards. Note, however, that there are always losses in the clutch when it's slipping, and the powertrain can therefore not operate in the low speed range for a long time. There is also a top speed limit, which in this example is 200 km per hour. The top speed is typically determined by factors which are not powertrain related, like high speed stability of the chassis or capacity of the brakes. It is the engine control system which prevents the engine to provide any torque above the top speed. We can now conclude that the powertrain has this total operating range in the force speed diagram when considering all gears, the top speed, and the possibility to slip the clutch at very low speed. Okay, let's stop here for now. In this lecture you have learned how the total operating range for a combustion engine powertrain can be derived from the engine torque speed operating range via the total ratio of the transmission at different gears. Before we go on to analyze what performance this powertrain can provide for a vehicle, you can do some exercises. See you soon.